Good morning. Welcome to Krishna's classroom. We begin with the 7th episode of Riemann integration. Last time I just ended with the problem I have listed here. And then also made some kind of remarks on how one attempts a proof of this. But I thought that probably it may be of interest to the students to know how these things are proved, because the proof is a bit intricate because it involves the supremum, infimum and all these ideas. And this is a place where you can see how the whole ideas are made use of. So let us start proving the first one. Okay. What is given? Both f and g are real valued functions bounded on the interval AB, where AB is a closed bounded interval. Now, what we say is the following. We are not assuming they are Riemann integrable or anything. But in any case, you see that the lower integral as well as the upper integral exists for f, g as well as f plus g, because f plus g also qualifies to be a bounded function on the interval. Therefore, it exists for f plus g as well. Now, the first inequality is concerning the lower integrals. Now, let us first analyze what exactly you have. Now, you see that suppose script P is the set of all partitions of let P belong to so P is a partition of P. Now what you know is that if you take all lower sums corresponding to F, you have got a collection of L, P, F for P belonging to the script P is bounded above and has a least upper bound. And you know that this is, we didn't designate this by the so-called lower integral. This is the lower integral. Designates similarly for the functions g and f plus g. So let us see what this means. What you have is this. See, look at it. So let us designate this point as the lower integral. It's a number. All the else are stay below that, and this is the least upper bound. So it's an upper bound. It's a least upper bound. If you choose an epsilon, then you can mark out a neighborhood of the point integral a to b fx dx as say, suppose I denote this by alpha, then this is alpha minus epsilon to alpha plus epsilon. What do you mean by the least upper bound? Given epsilon is, okay, there exists a P belonging to P such that what I mean to say is that there exists a certain P for which L, P, F lies somewhere here. No matter how small an epsilon you choose, you see that between alpha minus epsilon and alpha, you have an LP F. Okay, this is the important thing that you should realize, and we are going to use that. So this is true for both F. Okay, let me write this. What does this mean? This means LPF greater than. So let me use this for, say, P1, because we want to use different things. Similarly, for the same epsilon, there exists P2 belonging to P such that LP to G greater than integral, lower integral of. So it is in fact two different things. Now these values are different. For F and G, these two are different. So there is an analogous situation here. Says you have got some Gx Gx minus. So we have the second inequality and the first inequality. Now how do we connect it up? Integral, the lower integral of f plus g. And obviously the way in which you connect this is through the lower sums and the upper sums. Okay, before that, suppose that is both P is a refinement of both P1 and P2. Then we can write L P F is greater than integral A to B. This is because you see that when you define P1 or P2, when you define P1, LPF is something that is greater than LP1F. Okay. So you have this result L. So we are going to use, we have used this result. What next? Now one observes the following. See, we have to connect it up with the lower integral of f plus g. And lower integral of f plus g is the supremum of LP f plus g. So let us see how LP f plus g and LP f, LP g, three things are there, how they are connected. One observes that LP f plus LP g is certainly less than. This is because the lower bound of f plus the lower bound of g on any interval is less than the lower bound of f plus So this is the fact that we are going to make use of. Therefore, let us start working on this. Now you see that. You see, you have L E F plus G is greater than L E F plus L E G, and you see that you have this result. So this is certainly greater than integral a to b plus integral a to b, the lower integral of x minus epsilon. See, we have this result. Lower integral. Now the lower integral of f plus g dx is greater than or equal to g, which is greater than, and this is greater than integral a to b, the lower integral of epsilon. So eventually this is what you have, integral lower integral of a to b f plus g dx is greater than or equal to. So we will isolate this result. Simply isolate this result for clarity. And this is true for any arbitrarily chosen epsilon. So hence plus. Now I have written a few extra steps. I could have just jumped a few steps without any difficulty at all. But I didn't want to do that. I didn't want to do that because the reason being that this type of argument is something very typical. This type of argument is very typical in proving this kind of results. The way in which the epsilon comes, so what does this say? So as I have said, we have started with, see, the kind of supremum and infimum, wherever it is involved, the type of arguments that you have to put across is this. Therefore, we conclude this. So that completes the proof of 1. Now, I leave it as an exercise. And there you can see that the inequality, when you start working on the upper integrals, the inequality gets reversed. And the reason is this, okay, that the upper bound of f plus g is less than or equal to the upper bound of f plus the upper bound of g. And from there you argue in the same way, you get the result. Okay. Of course, you are working with the supremum, then you will have to work in the other direction. Okay, you will be working with not L. I'm sorry, you will be working with U, the upper sum. Okay, so you will be working with the upper sum, and you will have to develop a similar argument for that, which is straightforward. But it's a good exercise for you to learn the art. Now let us explore the third one. I don't want to prove it either, but you see that these are two results. It connects the lower integral with the lower integral when alpha is positive, and the lower integral is connected with the upper integral when alpha is negative. Now this is something to be understood. For instance, when you take alpha equal to -1, the lower integral of -f is equal to minus of the upper integral of f. Okay, so in particular that's which we may have to use. And an immediate consequence of 192 is the following. So we observe the following. Now one observes that integral a to b plus integral a to b dx the lower integral is less than or equal to the lower integral of f plus. But you know that the lower integral is always less than or equal to the upper integral. So this is less than or equal to integral a to b, the upper integral of and the immediate as a consequence of 2 you have this less than or equal to integral a to b, the upper integral of fx dx plus the upper integral of gx. Okay, so this is the chain of inequality that you get in any case. I am not making any further assumption on that. But suppose I am going to make another assumption. Now I assume f and g are Riemann integrable on AB. Then what do you infer? What you have is this. Then this is even only if the lower integral is equal to the upper integral of. Similarly, the lower integral of dx is equal to the upper integral of dx. Therefore, you see that what you have here is equal to what you have here. So this is equal to this is equal to this. What is the consequence? You see that integral a to b f plus g dx and this implies is equal to which in turn implies f plus g is and we also infer that everywhere in this part the equality holds. What does it mean? It means further you have Riemann integral of f plus dx is equal to so sum of the functions, Riemann integrable functions is Riemann integrable, and the Riemann integral of the sum is equal to sum of the Riemann integrals. So that is the conclusion that you get. So this is a consequence of 1 and 2. Now you can club it with 3 and show that f minus g is also Riemann integral. Prove if then f minus g integral and integral a to b f minus g. So these are those rules. But you should, if you approve, you will have to use part 3 of the above result. Okay, so that gives a wealth of results for us. Okay, so it can be extended further, and one can prove that the Riemann integral of alpha times the Riemann integral of dx. This is true for every. Prove this result. That would need this result. Use of this result. Well, that's very interesting. So it in turn shows that if you take Riemann integrable functions on the interval AB, then their sum is Riemann integrable, scalar multiple is Riemann integrable. Therefore, the class of Riemann integrable functions on AB form a linear space. So the summary of the whole thing is that if we designate the Riemann integrable functions on AB by strict R AB, then R AB is linear space over. This is one of the. So here I just put it here, bounded, and then RAB is a linear space. Okay, so that is about the structure of that. Well, now we proceed further and get some results using this. Now recall, when we introduced Riemann integration, we first considered non-negative functions, although it was not necessary at all. Made a remark about it and got over that problem. But it was done deliberately to give you some clarity about the lower sum, upper sum, etc. In that context, from that result, we were trying to work out the Riemann integral of a not necessarily non-negative function. In that case, we used the following. We said that given f bounded on AB, we can write f of x to be equal to f minus x where both f plus and f minus are non-negative bounded functions. How was f plus and f minus obtained from f? See, f plus was defined as the maximum of zero, and this we can rewrite as more explicitly it is fx where fx is greater than or equal to 0 and this is equal to 0 whenever. Similarly, f minus x is defined as maximum of minus fx 0, which is equal to minus fx wherever fx is negative and equal to 0 wherever fx is positive. You have seen the graph, what this looks like. Consider the graph of f as given in figure 1. Here fx is non-negative on some parts of the domain and negative elsewhere. Now f plus is defined as fx wherever f is non-negative and as 0 wherever f is negative. The graph of f plus x is marked in yellow color in figure 2. Now recall that the definition of f minus x is equal to minus fx wherever fx is negative and 0 elsewhere. To get this, first reflect fx on the x-axis as shown in figure 3. This gives the graph of minus fx. F minus x is defined as minus fx wherever fx is negative and that is equivalently minus fx is non-negative and 0 elsewhere. This is shown in figure 3 in magenta color. Figure 4 gives the consolidated picture from which one can see that fx is equal to f plus x minus f minus x. Now the sort of statements that I want to make are the following. The first thing is that if f is Riemann integrable, then both f plus and f minus are Riemann integrable. Okay. both non-negative functions belong to further. We have integral a to b So the second part is a consequence of the previous result that we have proved. So it is enough to prove that if f is Riemann integrable, then f plus is Riemann integrable and f minus is Riemann integrable. And if you can prove one of them, the other one can be proved in a similar way. So how do you do that? What do you mean by f is Riemann integrable? F is Riemann, these are the given facts. Given x and positive, here x is p partitions such that u p f minus l So can you prove this for f plus as well as f minus? One observes the following. See, what is UPF minus LPF? Let's do a little bit of working. I mean, this is how you investigate. See, you have UPF. We take P to be equal to B. That's the part. So, what you get is this is equal to sigma this is the sum where mi is the supremum of xi minus 1 xi and small mi equal to infimum of over x belonging to this one. Look at the definition of f plus. Plus, now you see that f plus is positive in certain places and it is 0 in certain places. Now, suppose your interval xi minus xi is such that the f is positive. If f is positive there, then you see the corresponding mi minus mi for f plus is going to be the same as this. Okay, it doesn't change at all because f is equal to f plus is equal to f, then f plus equal to f. Suppose both are negatives, something like this. So here, suppose you assume that this is your f. If both are negative, then you see that f plus is defined as 0 function here and mi minus mi for that corresponding function is going to be simply 0. So we are working on the 0 function. Now the third situation is a mixed one where you have suppose something like this and assume this is your mi and you see that from here onwards it is going to be 0. Therefore mi minus is going to be what? This is going to be equal to small mi in this case is negative. Therefore you see that this mi is less than or equal to mi minus mi because small mi is negative. That's the reason for that. Therefore, using this one gets from here that u P F plus minus L P F plus for the same partition is less than or equal to, and this you know F is Riemann integrable, therefore this is less than epsilon. So now forget about this part. It follows that given epsilon, there exists a partition which we have obtained from here such that UP F plus minus UP LP F plus is less than epsilon. Therefore, F plus belongs to Riemann integral. Similarly, to minus, now apply the previous theorem and then you get this result. We have observed that F, in fact it's a bounded function, given F bounded. We can define mod F. Once again show that if F is Riemann integrable, F plus mod F is Riemann integrable. Why it is so? If F is Riemann integrable, then F plus is Riemann integrable, F minus is Riemann integrable, and the sum of two Riemann integrable functions is Riemann integrable. Therefore, mod F is Riemann integrable. And it immediately follows this from this also. So we have seen that if F is Riemann integrable, then mod F is Riemann integrable. Might ask a question: is if mod F is Riemann integrable, is F Riemann integrable? Implying this is a question. So if F is Riemann integrable, mod F is Riemann integrable. But suppose there is a given F for which mod F is Riemann integrable, is F Riemann integrable. What is the counter example? Take F to be equal to 1. It's an improvisation from the Dirichlet function, x belonging to. That means at all rational points on the interval 0, 1, we define the function to be equal to 1. And at all irrational points, you define the function to be minus 1. And you can easily see that this is does not belong to R 0, 1. However, if you take what about mod fx? Mod fx is equal to 1 for x belonging to This is open. It's a constant function, and mod f is Riemann integrable. So you have to prove that f is not Riemann integrable and mod f is Riemann integrable. So this is an example. I have used this term. Now assume this Riemann integrable. Observe that for every x belonging to the interval AB, f is Riemann integrable on AB. That is, first we make this observation. I don't want to give the details of the proof, but how would you prove this result? How do you prove this result is by giving a sort of applying our characterization theorem. Produce at P, given epsilon, produce at P such that f is on a partition, produce a partition of the interval 0 to x such that UPF minus LPF for that partition is less than. Okay. So let us do that. See, make some observation. Now let me take C to be an arbitrary point on this. Instead of using x, I will use C for the time being. Now you see that I take a partition P. Now you know for sure that there is a partition. Now there are two possibilities. Now you see, certainly xi minus 1, xi is some partition equal to x naught equal to xn is the partition that you have. C belongs to I. Is it an interior point of that or on the boundary? If it is already on the boundary, then we set P equal to P1. If C is equal to xi or xi minus 1, take P1. Otherwise, we take P to be a refinement of P1 with the extra point C inserted. In any case, you see that you epsilon whenever this is true. So we always get UPF minus LPF less than epsilon whenever you take this additional point either as this or this, or set border points without loss of generality. Assume xi equal to c. Now define P tilde to be the partition Then what do you get? Immediately verify that u p tilde is less than or equal to and this is already less than epsilon, so we started with an epsilon, constructed p, from that we concocted the partition p tilde and we got this less than epsilon. Implies f is Riemann integral C is an arbitrary point, therefore we can say the same thing about over the interval a to x for any x. This is what it is. Therefore now define, because the integral exists, define f of x to be integral a to x. This is the area function. So we have successfully computed area function for all Riemann integrable functions. Recall the first 4 examples that we discussed and how the area function has been calculated. In those cases, the area function has been calculated using geometry. Split it into rectangles and triangles and then summed up and then worked it out. Here also we have done it. We have approximated the function from below by a step function, approximated the function from above by a step function, and then proceeded to the limit as the interval length goes to 0. That is what happens when you let n tend to infinity, and then we found that if these upper sums and lower sums go to the same limit, then you have the function Riemann integral. And for all such functions, we have defined area function. Okay. We also did one more thing. What was that? We verified that in all those cases, a derivative of x is equal to fx wherever a is differentiable. That's something that we proved, or we observed that. Therefore, you expect the same result here. Okay? You expect the same result here. What does it mean? If we were able to prove that wherever the function a is differentiable, then we have a appearing as an antiderivative of ft. Okay, that's it. Antiderivative. So we are connecting up the antiderivative with the area function in this case. Now this has been our objective. This is the sort of thread that we follow. What we expect. We have seen that we worked the fourth example that we looked at. We had a step function, and in that case, what happened? We got the area function. We found the area function is not differentiable at the points where f has discontinuities. Except at that point, we had the area function giving you the antiderivative in the sense that its derivative becomes the given function. Okay? So except at those points of discontinuity it happens. So we expect some such conditions to follow, but we have to rigorously address this problem. So the next investigations will be essentially towards this kind of result. You observe that the function a is show that ax minus ay is equal to integral y to x. That means for any x and y such that y is less than x, you prove that f is Riemann integrable and ax minus ay will compute to be equal to this. And then you can show that ax minus ay is less than or equal to integral y to x. Modulus of that that this is less than or equal to where m is the upper bound of given epsilon positive, choose delta to be equal to epsilon divided by m, so that is possible from this inequality. It does not, see, given epsilon, the choice of delta does not depend on the point x or y. It depends only on epsilon. Therefore, A is uniformly continuous. This we have seen. We start with a jump discontinuity function and then compute the area function. What do you end up with? You end up with a continuous function on the interval AB, and that is uniformly continuous. Okay, so that's the result that we have proved generally. Okay. I stop this talk. Thank you very much.